In this video, we learn to integrate fractions, particularly called rational functions, P over Q. Rational function is the division of two polynomial functions. So in this fraction, P and Q are both polynomials. Now, we're going to only focus on what's called proper fractions. What's a proper fraction? Well, in a fraction P over Q, say the order of P is m, the order of Q is n. When n is greater than m, higher order on the bottom than on the top, it's called proper. Now, if the rational function is not proper, what we can do is to do long division and simplify it as sum of a polynomial and a proper fraction. For example, so this is a quick review of long division that we learned in algebra. This is a partial fraction where the top is a third order, the bottom is second order. So I'm going to show you how to do long division to reduce this to the sum of polynomial and a proper fraction. In algebra, you put the divisor here, put the numerator here. Now the way I do it is to leave room, space for terms missing. Say we start with the third power, next we expect square. There's no square, so I have a space for square term, I have a space for first part term, then the constant. So this way when I do my work, all terms line up automatically properly. Alright, let's start to do long division. Let's compare the highest order term here, that's a third order, and the highest order term out here is second order. So what I need to do is to come up with a term on the top which when multiplied by x squared gives me 2x to the third power. Well, this is x squared, so I would need a 2 times x on the top. So it's the first order. It's the first order, so I put it on top of the first order. Then multiply. 2x times x squared, 2x to the third power as expected, 2x times 1 is 2x, and that's first order term, so I'm going to put it here. It's a 0 here. I just want to make sure all the terms are lined up properly. Then do subtraction. 0 minus 2x is negative 2x. 0, 0, so it's 0. And the 2x to the third power minus 2x to the third power is 0. And then move the next term down. That's negative 1 there. So this is a long division. Now this part is called a remainder. As we're doing this, we check each time we finish one step the order here. If the order here is greater than or equal to the order of the divisor, we continue this. If not, we stop. Well, This is first order. It's already lower order, so we're done. Now let's write down our answer. This is a quotient. We put the quotient here, and the remainder and divisor. Now you see the improper fraction is expressed as a sum of a lower order polynomial. When I say lower order, I mean it's definitely lower order than that. It's a polynomial, and a proper fraction. The order here is first order, this is second order, so the bottom is higher order. Now it's proper fraction. So anyway, when we discuss, integration of partial rational functions, we assume that this is a proper fraction. If it's improper, we can always do long division, and integral of the whole thing would be the same as integral of a polynomial, which is trivial, and integral of proper fraction that we want to talk about here. Okay, so P over Q is proper, assume. Now, how are we going to integrate fraction like this? Well, it depends on the denominator. Denominator is a polynomial, so our strategy is corresponding to different kind of denominator, we do it differently. Now, no matter what denominator we have, the idea is to somehow rewrite P over Q as a sum of simpler fractions. We call it partial fractions. Hopefully, it's possible to evaluate simpler fractions. How we decompose a fraction as a sum of a simpler fraction depends on factors the denominator contains. The denominator is a polynomial. In algebra, any polynomial can be factored as product of first order factors or second order factors. So depending on the type of factors involved, all just first order or second order. Depending on the kind of factors involved in the product, we come up with a different way to decompose the fraction. So this method is called a partial fraction. Now, we divide all the cases into 4. First, let's see what we do or how we decompose fraction when Q contains distinct first order factors. Say the Q contains ax plus b, cx plus d, or more. Now a, b, c, d are generally different, so they are distinct factors. With first order distinct factors in Q, what we do is to assume partial fraction as the following: constant A to be determined over one factor, a different constant B assumed over another factor, and so on. Okay, So it's a constant over first order. Constant over first order. Now, the rest is algebra. We would add all those fractions up, partial fractions up, and then somehow try to determine those undetermined numerators, parameters, capital A, capital B, or capital C. I'm going to show you through an example how to do that. Once it's done, then you would have numbers here. Then integrate both sides. Integral of the proper fraction P over Q would become the sum of integral of much simpler partial fractions. Let's see this example. So I have P, say constant. Q contains first order factor, different, distinct first order, 2x plus 1, x minus 2. So 5 over 2x plus 1, x minus 2. Let's first do the partial fraction. So first order, 2x plus 1 is the first order, so I'm going to assume a over 2x plus 1. X minus 2 is a different first order, so I'm going to assume b over x minus 2. Now, our job is to try to determine a and b, so both sides are the same. Then later, integral of this will become the sum of integral of each. How do we determine a and b then? Add them up. So we find the common denominator. Common denominator, the way we decompose the fraction, common denominator is always the same as this. So we just multiply top and the bottom by the missing x minus 2 factor, and here top and bottom by 2x plus 1. Then these are two factors with the same denominator, common denominator. Now top, we can actually just multiply through and put them together. Ax, 2a, 2bx plus b. And then combine like terms, collect coefficients of x terms. There's x, there's x. So we have a and the 2b as coefficient of x. Negative 2a and b together will be the constant term. Okay, so whatever partial fractions you assumed on this side, add them up by finding common denominator, multiply it out, combining like terms, make sure you get your numerator in the form in which powers of x are in descending order. Then you compare this to the left side that you started out with. Now how to compare? Well, we want to, remember, determine those A, B, or C or more, so that those two fractions are the same. Well, when you compare those two fractions, the denominator are already the same. Therefore, the numerator must be the same. Normally, you see a much more complicated polynomial here, and this is a polynomial involving whatever parameters A, B, or C. So for those two to be the same, coefficients of like powers of x must be the same. With this in mind, then we see, okay, we're going to pick up our AB so that A plus 2B on the right side, which is coefficient of x, must be the same as the coefficient of x on this side. In this example, there's no x. It means A plus 2B must equal to 0. So if you pick up A and B such that A plus 2B is 0, well, the first order terms match. Like there's no first order because we start out with a fraction with no x on the top. Similarly, the constant on the right side here would have to match the constant on the left side, which is 5. Okay, so practically you just set coefficients of like powers of x to equal to each other. What you have is a system of equations, 2, 3 or more variables. Then solve. All this you can see is pretty much algebra. How do we solve this? Well, I'm going to say determine AB using what's called elimination by addition. For example, if I multiply the first equation by positive 2, look, there's a negative 2a here. So if I multiply the first equation entirely by 2, I would have a positive 2a. Positive 2a and the negative 2a combined or added, a is gone. A would be eliminated. Okay? So first equation multiplied by 2, 2a plus 4b plus 2 times 0 is 0, call this equation 3. And then now second equation and the third equation added, it's gone, and 5b equal to 5, which means b is 1. If b is 1, look at the first equation. A is negative 2. Alright, so we determined values of A and B so that both sides are the same. Well, this is just the partial fraction, that's algebra. Our main work is to evaluate the integral. Let's get back to our main work. According to our algebra work, b equal to 1, a equal to negative 2. So the fraction itself same as negative 2, plugging for a, positive 1 for b. What it means is, okay, continue with our integration, our main job. Integral of this would equal to the sum of integral of each. Now you can see it's very easy to evaluate those two integrals. The first one, with a simple substitution, 2x plus 1 equal to u you can easily find the answer. So you pull out the -2 with the substitution. You have 1/2 because of the substitution. Being negative times half is -1, and this is log u. Just this part. I'll work on the other part. Be log 2x plus 1. For this part, okay, similarly you do x minus 2 equal to v at different substitution. You would have 1/v dv. This case you have log v plus c, or log x minus 2 plus c as the answer. Alright, so this is the first case for denominator involving first order distinct factors, different first order factors. We assume constant on top of each first order and do the algebra that I show you here. Finding common denominator, add them together, simplify the top, combining like terms and so on, then set coefficients of like powers of x to equal to each other, and solve to find the values of parameters. This way can rewrite the original fraction as a sum of partial fractions, simpler fractions, and do the integration. Once we come up with the decomposition, then it becomes integral of simpler fractions. Then you do whatever integration work we have to do, technique, formula, whatever. So this is the first case. Let's see second case, when the denominator contains repeated first order factor. See, denominator q is a polynomial. Polynomial can be factored into product of first order to second order. It's possible you end up with repeated factor, like a first order, identical first order. So it will become a first order raised to some power k. Alright, let's see. What if q contains ax plus b to the kth power, among other things? Well, just corresponding to this repeated factor or multiple factor with the multiplicity k, the p over q should contain a1 over ax plus b, a2 over ax plus b squared, a3 over ax plus b to the third power, all the way up to ak ax plus b to the kth power, and other partial fractions that corresponding to other factors. So though these k partial fractions are all corresponding to this repeated factor. There are k of them, so I assumed k different parameters using subscript a sub 1, a sub 2, a sub 3, a sub k, like A, B, C, D, E, F, G, depending on the number k. Alright, so let's see one example here. Our fraction contains denominator with the first order x minus 1, which is a repeated factor with a multiplicity of 3. So let's first do the algebra. X to the third power minus 4x minus 1, x minus 1 to the third power. Alright, most important thing is to come up with the correct decomposition on this side. Once we have that, it's all algebra, sometimes complicated. Okay, so I have a x which is non-repeating, first order, so I'm going to assume a over x, and x minus 1 is a repeating factor, so I'm going to have a factor with x minus 1 on the bottom. I'm going to have a factor x minus 1 square. I'm going to have the third power up to the third power, because that's the original power in the denominator. Okay, I got up to k. Alright, on the top we need 3 parameters. I can call the b1, b2, b3 with the same b, maybe just to show better they're all because of the same factor, x minus 1. Or I can just use b, c, d, doesn't matter because there are only 3 of them. Okay, well, the rest would be to combine them into a single fraction. It's the same algebraic work. We're going to find the common denominator, which is actually here. So what you do is to rewrite each every one so that the common denominator becomes a new denominator. For example, the first one I would multiply top and the bottom by x minus 1 to the third power. Now compare x minus 1 to the common denominator. I would have to multiply the top by x and the square. Here, top by x and x minus 1. The last one, top and the bottom by x. So you see, got a common denominator each every fraction. So add them up. Now, it's all algebra. I'm not going to spend time to do a lot of those detailed algebra work. So what you do is to expand this product's powers and multiply through and combine coefficients of the like powers. If you do that, you're going to in the end get a plus b x to the third power. This is a problem example in the book, so I'm just copy them. The result. Okay, once again, from this to this, you multiply everything, put them all together, group powers of x, the same power of x terms, like third power terms together. Oh, this is square. Second power terms all together, and then factor out, you would end up with this. Okay, so just like the previous example, now we have two fractions that must be the same, depending on how we pick up the coefficients a, b, c, d. Well, since the denominators are already the same, for the top to be the same, the numerator must be the same. For numerator to be the same, coefficients of the same powers must be the same. So again, we require a plus b, which is the coefficient of x to the third power, to be the same as the coefficient of x to the third power, which is 1 here. And the coefficient of x squared here on the right side must be the same as the coefficient of x squared, which is 0. Similarly, 3a plus b minus c plus d as coefficient of x must be the same as the coefficient of x here, which is -4, and -a, only constant term, must be the same as the constant -1 on the other side. So we got a system of 4 equations, which is normal. There are 4 parameters, a, b, c, d. That's all. This is all algebra, and usually system of 4 equation is complicated. Even system of 3 equation is bad. In this case, it's not so bad because we kind of can tell a equal to 1 right there. If a equal to 1, b equal to 0. Now with a, b determined, we can figure out the c here, right? So c would equal to 3, and you just with a, b, c, d determined, you can determine the d, which is -4. Alright, so now we going to get back to our main work, that is to integrate this fraction. Okay, well, according to our result, x to the third power minus 4x minus 1 times x minus 1 to the third power equals a over x, b over x minus 1, so on, and a, b, c, d are determined. So we actually have 1 over x, 0 over x minus 1, 3 for c, and -4 for d. Okay, and now integrate. This term is gone, so integral of this becomes integral, the sum of the integral of those 3 little guys, partial fractions. Over x, 3 over x minus 1 squared, 4, well, I can actually pull out the 4 too. Okay, well, basically now it's just a simple matter of substitution. In this one we get it directed as log x, or this one with a simple substitution u equal to x minus 1, very simple integral. I'm not going to repeat the work here. Okay, it's a simple substitution, and this is a simple substitution too. Alright, so this whole idea again is to try to decompose a fraction into partial fractions, simpler fractions that we can easily integrate. The idea is to try to come up with the correct structure on this side. So in this case, we focused on repeated factor. The repeated factor, then first order. Then we have to assume accordingly partial fractions. The way it works is if the multiplicity of the repeated factor is k, you're going to have a k factors just because of that. If there are others, like in the example there's x non-repeating, we of course do it accordingly too. That's like a case 1 factor, non-repeating first order. Okay, non-repeating, repeating. Okay, let's move on to case 3. Remember again, any polynomial can be factored into first order, second order. The first order can be distinct, non-repeating, case 1, or repeating, case 2. It's possible we see second order factor, irreducible second factor, like x squared plus 4, cannot factor anymore. Or sometimes you see second order, that's actually not second order. In this case, you could continue to factor. So we're not talking about this kind of second order. We're talking about irreducible, impossible to factor, to further reduce. So, alright, what do we do if Q contains, for example, ax squared plus bx plus c, among other things, like a first order repeating or non-repeating? Well, what we do this time is to assume ax plus b over this guy and other partial fractions corresponding to other factors contained in Q. Okay, so it's ax squared. So this is the new guy, second order, with a first order involving undetermined coefficients a and b on top. Of course, if there's another different second order, we would assume cx plus d on top of that. Okay, let's see one example. So the fraction is x plus 4 over x to the third power plus 4x. First of all, we need to factor the denominator to see what kind of factors the denominator contains, because corresponding to different factors in Q, we assume different partial fractions on the right hand side. Well, factor of x squared plus 4. It's easy enough. X squared plus 4 is irreducible factor. It's a second order. This is the first order. So we have one first order, one second order. Well, for first order non-repeating, it's simply a over x. Just some constant to be determined. For second order, we assume bx plus c over this second order. Okay, the first order over second order, zeroth order constant term over first order. So order on the top is always one less than order on the less than the order on the bottom. Well, the rest will be similar to the previous examples. The last two examples, we would find the common denominator actually here, and combine them, simplify, and set the coefficients of the like parts the same. So let's do that. We combine those two fractions. We multiply top and the bottom by x squared plus 4, and we combine. We multiply top and the bottom by x. Multiply out ax squared plus 4 bx squared, oh there's 4a, plus cx over just denominator, and combine x squared terms. There's ax squared is bx squared, so I have a plus b x squared. Now x terms, there's only one x term. Constant, there's only one constant, 4a, over, now I want to copy down the denominator for better comparison. Denominator will not change, it's the same common denominator. Now again, I simplified the right hand side as a single fraction that I want to compare to the original one there. So denominator the same, numerators must be the same. Let's start with the coefficient of x squared. Coefficient of x squared is a plus b. On the right, coefficient of x squared, 0 on the left, and the c is coefficient of x, 1 is coefficient of x, so c equal to 1, and 4a equal to the 4. 4a constant here, 4 constant there. Again, normally we end up with the system equation, 3 of them, 3 variables. This is a rather simple equation. C equal to 1 already here. Here a equal to 1. Now if a is 1 from the first equation, b equal to negative 1. So what this means is our original fraction x plus 4 over x to the third plus 4x equal to a is 1, so 1 over x, b negative x plus c over x squared plus 4. Okay, those are the two partial fractions. Now integrate with the dx, with the dx, with the dx, of course. Okay. Well, the first integral is trivial, it's log x. The second integral is not obvious. We have to split the fraction into 2 because we treat them differently. Okay. First, negative x divided by x squared plus 4. I already got the negative here. And then 1 over by itself. Alright, log x copy down. This integral, we can use a substitution, x squared plus 4 equal to u, because check it out, if you differentiate both sides, du would equal to 2x dx, like x dx, I get the supporting factor like how we do, substitution all the time, get perfect substitution factor. It should work. Go through the detailed work. Have 1/2 log x squared plus 4. Just straightforward, simple substitution. And this one, you cannot do substitution. You cannot assume u equal to x squared plus 4 because there's no supporting factor x on top. As a matter of fact, this is inverse trig related. Remember, x squared plus 2 squared. So there's a formula. It's just 1/2 inverse tangent to x. No, actually, sorry about that. It's x/2 here. This is x squared plus a squared. The formula x squared plus a squared is 1/a inverse tangent x/a plus c. It's 2 plus c. Alright, this is the final answer. So this is case 3. The denominator contains second order factor. Second order factor in the decomposition construction at first order polynomial with undetermined coefficient is assumed on top. The other factors involved, you assume other partial fractions. The algebraic work we went through is always the same. Combine, simplify, arrange powers in descending order, parts of x. Then set coefficients of like powers to equal to each other. One by one, you end up with a system that you solve, you determine coefficient. So the original fraction becomes a sum or difference of partial fractions. In this case, your second integral corresponding to actually your second order factor must be split into two separate ones because different technique is needed for different part. This part always simple substitution. For this part, it's always inverse tangent. You just have to be careful with the a square. Sometimes there is a number in front too. Remember, in that case, you would have to rewrite. We talked about this kind of integrals before. So this is case 3. Denominator contains second order factors, distinct second order factors. Now, the fourth and the last case is when the denominator contains a repeated second order, okay, multiple second order, identical second order. Say you have a p over denominator q, have ax squared plus bx plus c raised to the kth power. Just corresponding to this factor, we would have to assume k partial fractions. Remember in case 2 we had repeated first order. We had to raise the powers. First order repeated k. Since those are all first order, on top we assume different constants, first order factors, zeroth order, I'm sorry, constant is zeroth order. So now with the second order on bottom, we're going to assume a1x b1, a2x b2, akx bk. So they're all first order. Each is each contains 2 undetermined coefficients. The order of each is always 1 less than order of the bottom, which is second order. So it's first order on top of second order. So there are a lot of undetermined coefficients involved this time. For this reason, we're not going to actually work on any problem to finish up the algebra involved to determine those coefficients. Because think about it, if it's repeated second order, you're talking about at least the fourth order here. That alone is already very complicated. You would have that. Plus, in many cases, you may have others, like a different second order non-repeating, or first order, or first orders non-repeating, or first order repeated. Just horrible. But the idea is, you need to know what to do. Don't have to actually do it because it's just so horrible. For example, I can make up a situation, say if you have an integral, okay, x to the third power minus 2x squared plus 4x over x minus 1, 5x squared plus 3x minus 1 to the third power. We're not going to finish up this. Just want to show you what kind of partial fraction you would have to assume. Well, let's see. Here's a non-repeating first order, and of course the key is this repeating. Okay, so we would have to assume, well, constant over x minus 1. That's easy. This is like case 1. And then starting from this guy, this is a third order. Well, actually, I would have to verify that this cannot be factored. I just made it up. So actually, I'm not going to go through all this. Let's just say cannot be factored. Let's assume cannot be factored. Okay. I would probably have to change the number. Anyway, let's just assume cannot be factored. So we would have to have a partial fraction, 5x squared plus 3x minus 1 reach the first part. 5x squared plus 3x minus 1 reach to the second part. 5x squared plus 3x minus 1 reach the third part. Now on top of each, there's going to be a first order b1x plus c1, b2x plus c2, b2x plus b3, c3. I could use a, b, c, d, e, f, g, h, but doesn't matter. It's different letters we use. What I want to show you is just how we assume appropriate partial fractions in the in the decomposition. This guy corresponding to first order, and these three corresponding to that. Well, you can imagine the algebra involved in order to really work this out. Just practically too complicated. The cases we need to actually work out everything will be the first three cases. Case 1 again, first order non-repeating. Distinct ax plus b, cx plus d, assume constant on top, a over 1, b over another. Case 2, repeating first order. Hopefully the case not too big. If it's too big, of course the algebra involved, you can imagine, would be again practically too much. I talk about k equal to 2, k equal to 3 at the most. So with the repeating, you just raise the power of this guy. On top of each, assume a constant to be determined. This is case 2, repeated first order. And case 3, second order non-repeating. Each case, the algebraic work involved in principle is the same. Once you come up with the correct structure, you just find the common denominator, add them up, sort things out, and multiply all things, combining like terms, like powers, then compare both sides. Set coefficients of the same power to equal to each other, end up with a system of equation of 2 or equation of 3 or more, and solve. You find the values of these parameters, so the original fraction becomes sum or difference of a simpler fractions. The integral of this becomes the integral of those guys, and those guys usually are integrable, meaning easy to integrate. Okay, so this is how we integrate rational functions using the method of partial fraction. Again, we only talk about proper fraction. This partial fraction method works on proper fractions only, but that's okay. If it's not proper, if it's improper, we could always do long division to split this improper into two parts. One polynomial. Polynomial is easy to do anyway, and second part, which is improper, and that's the kind of rational functions we discuss in this video.